All right, so welcome to the Generalized Linear Modeling Workshop. I apologize that this video is coming up a little bit later than had originally been anticipated. When I looked at the video from our initial help session, or our initial R-bootcamp session, I had not recorded the screen properly, and so the video did not clearly illustrate what I was doing in the R Markdown document. So in light of that, I'm re-recording the video in my office. I'm going to try my best to remember some of the issues that came up during the R Bootcamp workshop so that I can include those helpful tricks here. But of course, if you have any questions or concerns about what you're seeing today, you can always reach out to me by email. This website that I have displayed is the place where I'm hosting or posting all of the content from the different R Bootcamp workshops. And so if you're interested in following along, you can download the R Markdown file there, as well as the data file that I'm using. And finally, you can complete the workshop survey, which would be absolutely fabulous. All right, so this data set is actually something that I had a lot of fun with. I'm currently looking at different places to live, and so I was wanting to find out what kinds of characteristics contribute to a home's value. And I found a publicly available data set online through Kaggle. There are all kinds of different sources for publicly available data sets. And so this set of data contains characteristics and price values of homes that recently sold in Ames, Iowa. That's just the location that was available to me. So when I first start any kind of a statistical project, one of the first things that I like to do is load all of the libraries that I'm going to be using. I've provided some background information about these libraries up here. And next I like to load in the data. So I've just assigned it through this read.csv command to a variable called house. Now, there are certain things that you can do with the read.csv command. If you're only interested in certain rows, you can do a read.csv and subset your file. For example, adding this bracket with 1 through 10 at the end will select the first 10 columns of the houses.csv file and load them into this data frame. Likewise, you can also do things like this, where you omit certain segments of a file with the -c command. There are different options that are available depending on what your data needs are. But for today, we're just going to download the entire data frame. Now, one of the reasons you might not want to download the entire data frame is because, or the entire data set into a data frame, is because often we end up with data sets that have a lot of variables, and you might not be interested in all of these. This format, the summary, is sometimes an overwhelming way of looking at things. If you need to know summary statistics about your variables, such as what kinds of values they take on, how they're being coded, and you want a lot of detail about it, the summary command is a really good choice. But if you're just interested in looking at which variables are present in your data set and what kind of a format they come in, the structure command is actually better for that. When you run the structure command, it tells you that you are pulling values from a data frame. It tells you how many observations you have and how many variables you have. If you have R Markdown, you actually also have that information over here, so you can see that the house data set has 1,460 observations of 81 variables, so that checks out. But then we have information about each of our variables, what kind of a variable type it is, as well as some sample values that it takes on. And this sort of condenses all of that information into a more succinct format. Another thing that I found is that sometimes maybe you want to look at all of the different levels of a categorical or a string variable like neighborhood. And if I were to say, do something like this, summary house neighborhood, and run that command, okay, well, I can see it this way, this is very helpful, but if I had lots and lots of variables or lots and lots of levels in that particular, many variables in that, or levels of that particular variable, I'm sorry, they might not all show up in a summary command. So you can actually use the tidyr and the dplayer libraries to do things like distinct house neighborhood. Well, now we have a list of all of the neighborhoods that are included in this data frame. Now, one of the things that's interesting about this data set is that it lists all of these house values by neighborhood. And of course, one of the assumptions of conducting a general linear model or even a generalized linear model is that our observations within our data set are independent of one another. If we mouse over to our data frame here, whatever house is being ID'd by number 1, the values for that house, how large it is, what kind of street it's on, what neighborhood, what condition the house is in, etc. These should be unrelated to those things about house number 2. But I think we all know from having lived in different communities that often the houses within a particular neighborhood are similar to one another. The people who live in them may have a particular kind of upkeep that they want to expend on their house. So some houses and neighborhoods are better kept than others. And similarly, we might have a neighborhood full of cookie cutter houses where they all have similar siding, similar floor plans because they were built by the same builder. So there's actually some dependencies built into this data set that could be handled through multi-level modeling that nested by, say, neighborhood. But we're not going to focus on that right now. Instead, we're going to continue on with our with our data set. Now, if we wanted to sort of like look to see, maybe we want to know the average home value in one of these neighborhoods, that might be an interesting piece of information because, of course, some neighborhoods have homes that are of higher quality than others. So what I've done here is I've used something called piping. Piping just means take the thing on the left and then use it to do the thing on the right. Very simple. So I said take information from the house data frame and use it in a group by function. So group this data by neighborhood. And then take those neighborhood groupings and for each neighborhood grouping, calculate the average value of the sale price, the average selling price of these homes. I've used the NARM command here in case I have some missing values in sale price. And here I've just assigned this mean sale price to a variable called average value. And when I run that command, now I can see for each of these neighborhoods what the average home value is. If I were interested in using that in a separate analysis, I would have to take this string and assign it to some variable, maybe something called A. If I do that and look over here, well, now I have a list of all of the neighborhoods and the average value of homes in those neighborhoods. And as you can see, there are some neighborhoods like Meadow Valley maybe, that are worth substantially less than other neighborhoods such as No Ridge, an interesting name, or I don't know what that is, North Ridge Heights maybe, something like that, which seem to be populated by higher priced houses. Okay. So we've talked about the data set, we've talked about how to pull summary statistics and other valuable information from a data set. Now let's actually run an analysis. And for me, I'm really only caring about a limited number of things about a house. I want to know how the lot size, the number of bedrooms, the quality of the kitchen, the type of home it is, so is it a home, a condo, an apartment, the year it was built, the finished basement or not, and the overall condition. How do each of these variables contribute to the selling price of that home? So one of the first things that I like to do, especially in this case, is I like to think about what I want my model's intercept to represent. And if you center your variables, the intercept is going to represent the average home value within your data set. That's something that I would like, because now I can look at how each of these variables impacts the cost of the home relative to that overall average. So for example, how does a home with 4 bedrooms differ in price from the average value of a home within my data set? So an easy way to do that is by using the scale function. Here I can just say that I want to scale a particular variable within my data set. To center it, I can just say center equals true, scale equals false. If I wanted to scale that variable, it would actually mean center it and then divide by the standard deviation of the values in that particular column. But for this purpose, I don't need to scale any of these variables, so I'm just going to run a traditional scale command with centering. Now the other thing that I'm doing here is I'm coercing this into a format that can be used by some of my other statistical analyses or other packages that I'm going to be used later. It's sort of complicated to explain, but basically if you just run the scale command and you reassign this to some variable, that variable will be recognized by some libraries and packages, but not by others. Not entirely sure why that is, but if you coerce this into a numerical format instead of a matrix class, it will be recognized by those other packages, and you can do that just by sticking C on the outside of those variables. So I can run all of those functions, and then here I'm effect coding all of my variables that are categorical in nature, which again forces that intercept to the average home value. Now you could mean center in many different ways. You don't have to divide by the average value. That just means that your intercept is going to represent the average home value in your data set. If you wanted to say, look at how the number of homes differed or changed the price of a home, how the number of bedrooms changed the price of a home relative to, say, a $100,000 home, well, now you just take this variable and you subtract 100,000 from it, and that becomes your centering. So whatever you want your intercept to represent, that's how you handle your centering. And of course, if you don't do any of this, then your intercept represents your holdout condition with any of your dummy coding, or it represents the value of your dependent variable that will be taken when a continuous value is set to 0. So, you can do whatever makes most sense for your data set. So I've started here by running a simple linear model. And one of the things that I like to do is to just run model comparisons. So to construct a model that I think is going to answer my question, and then I just don't even interpret the model. I don't look at significance. I don't peek in any of the findings. I just start looking at different characteristics of the model to determine whether it's the appropriate model to answer my question. And in doing this, it saves me a lot of trouble because now I don't have to make the hard decision between which model I like the most. Is it model A or model B? Once I know, what the ultimate findings or results would be from each of those models. So here I've used the plot command to plot the residuals from this model. And this is something that Evelyn and Angela covered in greater depth in the general linear modeling section. So if you want to learn more about how to plot different ways to plot residuals, you can go back and watch that video. But you can see that we have a homogeneity variance problem. Anytime you're running a linear model, we're assuming that our residuals are going to be evenly distributed around some value or around the line of best fit. You can see that there's very little variability in our residuals at the smaller end of our data set, at the lower value homes, but as we look at homes of larger and larger value, well, now our residuals become more variable. And part of this is just because we don't have as many observations out here at the upper end of the space. Now this is something that is very common for dependent variables that have skewed distributions, things like price, where the cost of a home can't drop below 0. And so we end up with this skewed distribution where there's a bunching of values at the lower end of the price continuum, and that extends into an upward tail. So that's one of the benefits of running a generalized linear model. We can specify the nature of that error distribution. We can say, hey, guess what, model? We know that there's going to be less variability in our residuals here and more variability in our residuals here, and it will conduct an analysis that models that. And so here we can run the same model. The only difference is that now, instead of running it as an LM or a linear model, I'm running it as a GLM, a generalized linear model. And now I have one additional command after I input all of the information about my model and the data set that I'll be using. It now asks me to specify the family. Of course, there are many different kinds of families of link functions. Here I'm using the gamma distribution because it recognizes that skewness of the residuals. And now when I plot my residuals, it looks a little bit better. I mean, it's still not perfect, right? We still have more variability out here because we have fewer data points than we do here, but this does not look nearly as bad as this did. So we've solved one problem. Excellent. Now we can actually start to look at our model. And we can see that there were a whole bunch of significant effects. Oh boy, that's exciting. But all of our estimates are in a transformed space. One of the things that happens when you run a generalized linear model is that it performs a transformation on the x side of your equation. Normally we think about transformations on the y side of an equation, like a log transform of our dependent measure. Well, now we're transforming the x side. So now all of our estimates are complete gobbledygook that don't really make a whole lot of sense. But we can fix that. It's okay. It turns out that the inverse link function for this generalized linear model is the inverse, so 1 over our estimate. So we can just keep that in the back of our mind as we're going to be plotting the rest of our model. So I'm going to only focus on 2 variables. I'm going to focus on how the year that the home was built affects its value, as well as how the quality of the kitchen affects the value of the home. So the generalized linear model tells me about the effects of continuous variables. So the number of bedrooms. This is a value. I can see how that value ranges along a continuum. But when I'm looking at a categorical variable like kitchen quality, it tells me what the estimates are for 3 of the values or levels of kitchen quality. But there's that 4th level that's my holdout level coded as -1, -1, -1 that I can't estimate. I mean, I could if I went through and did all of the calculations, but it's not providing me with standard errors of that estimate, etc. So one thing I could do is I could hand calculate this if I wanted, or I could just use the em_means command to run that particular model. So here, if you just run em_means, it produces a wonderful little data frame that you can use. But again, you can't actually access the numeric values from that data frame. If I were to try to use this, assign this em_means to a variable like kitchens, it wouldn't allow me to extract any of the numbers from it. So I can actually wrap this in the summary function. That produces something that looks very much the same, but it's actually a slightly different structure. And if I assign that to the kitchens data frame, well, now I have a data frame that contains all of this information. Hooray. I can use this to construct a plot or a graph of these effects. Whenever I'm using ggplot, I like to run through the commands incrementally. I like to think about creating a graph the same way that, if you were an artist, you might think about creating a painting. First you paint the background, then you go in layer by layer and you add additional detail. And it's very much the same with ggplot. When you start doing a ggplot, you call a command that tells it about its aesthetics. So what do you want the background of your graph to look like? You provide it with information like what data set you're using, which is just going to be this kitchens data frame that I used before. And then you set these aesthetics. What do you want on the x-axis? Well, I want kitchen quality to be on the x-axis. What would you like on the y-axis? Well, I'd like the em_mean to be on the y-axis, that em_mean being the price value, average price value of a home given its kitchen quality, but Since we ran a generalized linear model, I have to back transform this by taking the inverse of the EM mean on my y-axis. And then because I like pretty colors, I like to maximize the data to ink ratio. Maybe I also want to fill my bars of my bar plot based on the kitchen quality. So the first thing I'll do is just run this first command. When you run that command, you should end up with a canvas that looks like what you want it to look like. Here I have my kitchen quality on the x-axis. I have that 1 over my EM mean on the y-axis, and these look like values that homes might be priced at. So far, so good. Now I can start to layer things onto this graph. The first thing that I'm going to layer onto the graph is a bar, a geom bar. You need to tell it what you want that geom bar to be based on, and because I'm specifying stat equals identity, it's going to look at what is being plotted on the y-axis and use this value as the value for each of those geom bars. Now I could just run this, and if I do that, I end up with something that looks like this, where I have the average home value for each of these kitchen qualities, plotted as a function of kitchen quality. But again, I'm picky, so I like to do all kinds of aesthetic things. I can actually change the width of these bars using the width command. If I rerun this, now my bars are a little bit narrower and they're not touching quite as closely. So there are all kinds of additional features that you can adjust there if you want to. Finally, because I like to know variability, I'm going to add some error bars to this graph. You can do this using the geom error bar command, where you specify what the minimum and maximum values of the error bars will be. And so here I'm saying that I want that minimum value to be the inverse of, because remember, we're operating in that transformed space, so the inverse of the lower confidence level from that EM means that I assigned to the kitchen's data set. And I want the maximum value to be the upper confidence level from that data set. Now if I were to run this, I'll end up with something that looks like this. And here the width of these geom error bars is equivalent to the width of what each of these bars would have been had I not changed the width of the bars in my function. But again, I like to be particular and I like things to be aesthetically beautiful, so I'm actually going to modify the width here so that it's not exactly the size of the bar, but actually slightly lower than it. Now if I run that command again, well, now I have beautiful error bars on my graph. Now if I wanted, I could assign all of this to a variable, and now if I ever call that variable, it will plot that graph again. But I can also use this to, again, plot some basic graph and then layer on things so that I can see what it looks like in different ways or with different characteristics. So here I'm trying to format this bar graph into APA style. So APA style, we can't have any of this gray garbage in the background. And in addition, since many of the people I work with are a little bit older, myself included, I like to make my axis labels a bit larger so I can see them. So Theme Classic by itself will strip all of that stuff, that gray stuff, out of the background. If I add this base size equals 14, well, you can watch what happens to the size of that label. Now all of my X and Y axis labels have gotten much larger. Now this over here, this kitchen quality, is displaying superfluous information. It's redundant because the kitchen quality is already being provided on the x-axis. So I can have guides fill equals false to remove that label from my graph. So far, so good. And maybe I want to change the X and Y axis labels into something that's more reasonable. I can do that with the labs labels command. I can say I want Y to equal the sale price of the home and X to equal the kitchen quality. So I do that. Now my graph looks beautiful again. How wonderful. Now let's imagine that I want to overlay the average home value on these graphs. Well, I know that this is equal to my intercept. So I have my generalized object, which is where I assigned my model. If you run the coefficient command around generalized, it gives you all of those coefficients that we saw before. So all of these numbers that were estimates. And we know that the intercept here is representing that average home value. So I can select the first number from the coefficients of generalized. And when I do that, I just get the intercept value. Now I want to take this value and I want to coerce it into a numerical value so that I can graph it. When I do that, I lose the header and just obtain the value. And remember, I have to take the inverse of it because we're in that transform space. And when I do that, I end up with the average home value for my data set. Now I want to plot this as a straight line on my graph, and I can do this using the function of x formula. I can create a function of x where, for a given value of x, I plot the stuff in these squiggly brackets. And since I want to plot the same value for all values of x, I just take this number and assign it to, or take the function x of this number and assign it to a value like intercept. Now I can take that basic graph with the classic theme and the resized text. I can change and remove those guides, fix the labels, but then I can add this stat function command. So add or layer a function onto my canvas. And here my fun function is going to be intercept, that function I previously defined. And because I like aesthetics, I'm going to make that line type dotted. When I run this command, well, now I get something that looks like this, where the average home value is plotted as a dotted line across my graph. Now let's say that I wanted to change some colors. Well, now I can take the graph that I previously made, assign it to a variable graph, and then I can add in Scale Fill Manual. Scale Fill Manual will allow me to change the colors of my bar graph, and I can assign very specific values. These are hexadecimal color codes. When I run that, now it's K-State purple colors. Now we had a question here come up during the session about whether there was a way to force these x-axis labels or these categorical variables to take on a different set of values, because here they were just appearing in alphabetical order, and maybe you didn't want that, because here we have excellent, fair, good, and then I forget what TA stands for, but you know, maybe we wanted good to be in between excellent and fair. That makes a lot more sense. Well, you can do that using the scale x continuous command, which I'm not going to go into now, but if you go into the help menu in RStudio and type in scale x continuous, or if you come down here and you just type in double question mark scale x continuous, these will both pull up the same thing, which is the help file for position scales for continuous data on x and y, where you specify x for the x-axis and y for the y-axis. And there is a way that you can coerce the R markdown file or the ggplot to display your categorical variables in a particular order. All right. So hey, fun stuff. Oh, and a quick note about hexadecimal color codes. I've provided a website here that will allow you to select colors from this beautiful display, and it'll tell you the hexadecimal color code. So you can do it this way, where you say, oh, I really like this, I don't know, vomit color, and here's the hexadecimal color for that. Or you can pull this drop-down menu and you can sort of play around and say, actually, I want something that's more green than that. Oh, that looks wonderful. Now I can get info on that. And here's that green color that I was looking for. In addition, there are wonderful websites out there that include information about what colors palettes are good for people who are colorblind. You might want to think about your viewers here. I've actually downloaded one of these images here. You can't see it very well, but here, these are all different color palettes that would be distinguishable by someone who was red-green colorblind. which is sometimes helpful to know if you're providing or producing something for multiple audiences. All right, so last thing we're going to do, that continuous variable. Ordinarily, I thought I was going to have to create my own data frame with all of these different values of x and populate it with the coefficients from my model, but it turns out I found the effects library that will do this for us. We can use a variable called predictor, or a function called predictor effect, select the variable that we're interested in looking at and the name of our model. If we run this command, it produces something that looks like this, where we get all of the values of our y variable, our predicted values for the different values of year built or centered year built. And we can take that, coerce it into a data frame, and assign it to a variable so that we can use it in a graph. Well, now our ggplot is based on this data frame. On our x-axis, we want the years built, but we want to unmean center it. So we take our years built mean centered variable and add the average year built of houses. And our y variable is fit here, because if you look at our data frame here, it turns out that our fit, the predictor effects function, is already back transforming this for us the way that we would want it to be back transformed. So here again, we can practice just painting our canvas. Here our fit looks like it's decent values. We have our years built. These are reasonable values for homes given the data set. And now we can add on a geom line to this graph. If we do this, we get a nice little line that represents how home values have changed given the year in which the home was built. Now, you'll notice this fit variable here is constraining the view that we're seeing. It goes from 140,000 up to 180,000, and so this line looks a lot steeper than it actually is. And we'll come back to that in a bit. We might care about the region of error around this line of best fit, so how much error is there in our predictions. We can do that using geom ribbon. Here we're resetting our aesthetics so that the minimum value is equal to the lower 95% confidence interval from our predictor effects data frame, where the maximum value is the upper 95% confidence interval, and our line type equals NA. I'm saying the line type equals NA because sometimes it will plot this error region and then try to plot a black line around the error region. So you end up with like a polygon over your line that's outlined, which looks really ugly. Now, if we were to do this by itself and run this command, well, now we end up with this error region that is really dark and we can't see the line beneath it. So something we can do is we can set our alpha level to 0.04. Alpha just controls the transparency of a given component, and now this shaded region is much lighter, and we can see that line of best fit through it. We can use the scale y continuous command, remember from earlier, scale y continuous, to set the values that we want to limit the y-axis to, so 0 and $200,000. If we were to run this, now we see a reasonable fit, reasonable years built, but let's say we want to put commas in here so that people can actually read those values the way that they would think about dollar signs. We can add the labels equals scales comma command to our scale y continuous function, and now we have commas in our y values. And we can assign this to a variable, and then we can change that variable in meaningful ways. We can change it into APA style, increase the size of the font, remove any kinds of guides we have, and relabel that graph. Cool beans, that looks great. And then again, if we wanted to plot that average home value over the graph, we can do it like this. All right, well guys, that's everything that I have for you today during the session. Again, if you have any questions, feel free to reach out to me by email. Those of you who are watching this probably have access to my email. Otherwise, it should be at the bottom of this page. And I look forward to hearing from you and seeing the fabulous graphs and models that you end up producing.